Hello, I'm Haris Posidis from IBM Research, and together with my colleague Tom Parnell, we'll present to you SnapML Accelerated, Accurate, Efficient Machine Learning. We're both excited to present at PyData today, and would like to thank the organizers for their invitation and you for your attention. So let's get started. Next slide. So SnapML, or which is short for Snap Machine Learning, is a library for optimized machine learning, and it has been designed with two main objectives in mind. First, to accelerate and scale some of the most popular classical machine learning algorithms, accelerate the training and the inference of those through awareness at the system level. And second, to develop novel machine learning algorithms that provide best-in-class accuracy, in particular for applications at the business level. So this is an overview of the SnapML library today. Starting from the left top, the SnapML library was started with generalized linear models, in particular linear and logistic regression and support vector machines. We implemented accelerated CPU and GPU solvers for those. Then moving on to decision trees and random forests, tree-based models, also CPU and GPU solvers. And more recently, we have implemented a boosting machine. Early this year, we have released an improved version of this boosting machine. And more recently, we introduced accelerated inference engines for the tree-based models, such as random forest, decision trees, and boosting machines. So SnapML is written in C++ and CUDA, the core library. We have implemented Python wrappers that offer the APIs. We offer in all 6 models the familiar scikit-learn Python API. And it has been offered to the public as a free installation as part of the IBM Watson Machine Learning Community Edition. A short overview of the solvers that we offer today can be seen in this table on the bottom right. So for all of the 6 models, we offer accelerated CPU solvers, multi-threaded ones, GPU solvers for all, as well as multi-GPU solvers for the generalized linear models and the random forest. We also offer distributed solvers for the generalized linear models, and we are currently working on offering multi-GPU boosting machine solvers and multi-GPU and multi-node distributed solvers for random forest and boosting machines, which we hope to offer in the first half of next year. So with that, I would like to give it over to my colleague, Thomas Parnell, who will take you through the rest of the presentation. Tom?
Okay, thank you, Haris. Okay, so I'm going to start by talking a bit about how SnapML is distributed and how it's available today. So as Haris already mentioned, the core library is written in C++ and CUDA. And then we package that up into various different packages that the user can install. So firstly, in the top here, we have the Watson Machine Learning Community Edition distribution. So this is a set of Anaconda packed with GPU as well as MPI support. There are 2 packages. One is called Pi for SK, which is a SnapML with a scikit-learn interface for single node use. And then there's SnapML Spark, which is Apache Spark API for use in distributed environments. So both of these packages can be installed simply by saying conda install Pi for SK after subscribing to the WML channel. And then what we're working on now is a new distribution method, which is somewhat simpler. we're building GPU-only wheels, which we plan to upload in the public PyP index. This will be simply the scikit-learn API for SnapML, and it will be installable via pip install SnapML. Okay. Harris, next slide, please. Okay, so would like to talk about the key research innovations behind SnapML. So let me start with the GPU acceleration. That was our focus really in the beginning, was on how can we accelerate generalized linear models on GPUs. So we started developing new extremely parallel asynchronous coordinate descent algorithms, which map very effectively onto GPU hardware, as well as new algorithms which deal with the case when the data set is too big to fit in GPU memory. So these were some of the earliest research ideas that were going into SnapML in already 2017 and 2018. After that, we started shifting our focus towards distributed training. So what you can do when you have a really huge data set, when you have maybe a cluster of high-performance CPUs or GPUs-based machines. And we developed a new algorithm called ADN, Adaptive Distributed Newton, for solving generalized linear models in that kind of setup. So when you have like a terascale data set. And some of our initial demos with SnapML were focused on this huge data scenario. After that, we started thinking a bit about what if you don't have GPUs? What if you're in the cloud and you don't want to spend a lot of money on a GPU-based instance? How can we exploit modern multi-core and even multi-socket CPUs in an effective way? So that was some of the research we were doing in 2018, 2019. I'm going to show you some results with that shortly. Again, the idea is how can we train generalized linear models as well as other models very fast on modern CPU hardware. And finally, that brings me to our current work and very recent research, which is around ensemble methods. So we started there looking for how can we accelerate training of models like decision trees and random forests. So we designed new hybrid training algorithms, hybrid between breadth first and depth first search for training those kinds of models. And then we also started asking how can we improve the accuracy of models like boosting machines. So that was our most recent work into SnapBoost, which is a new boosting algorithm where we choose the base learner at each boosting iteration stochastically, so by sampling from a random distribution. And we show that using that approach, you can get better accuracy than XGBoost and LightGBM, but without sacrificing performance. Okay, next chart, please. Okay, so this is a little bit about the API, so we can show you how SnapML is used. So in this example, we compare training and evaluating a random forest on the left-hand side with scikit-learn, and on the right-hand side with SnapML. So you see, aside from the import, things look very similar. We have mostly the same parameters as scikit-learn, random states, max depth, n estimators, n jobs, max features. But we have some additional ones. Use histograms. This is a optimization that splits each node using histogram statistics instead of searching through all of the possible values, which can bring a lot of acceleration, as well as use GPU and GPU IDs, which tell SnapML whether it should use the GPU or not, and then how many GPUs to use and which IDs it should use. Finally, when we look at the actual training and inference, you see that it adheres to the scikit-learn API, we have fit, predict functions, we have predict, prober, score, and all everything that's defined by the scikit-learn API. Next chart, please. So similarly, we have the boosting machine here. As you may know, XGBoost has its own API, but it also exposes a scikit-learn adherent API called XGB classifier and XGB regressor. Here we show an example with the classifier. So you set an estimator's max depth, learning rate, tree method equals GPU to tell it to use the GPU, as well as the number of CPU threads and jobs. And on the right-hand side, you see the SnapBoost API. Again, it's very similar. Instead of setting the max depth, we can set a min max depth and max depth. This is part of the stochastic element of SnapBoost. It can choose the max depth at each iteration randomly between the min and the max. And we also support GPU acceleration via the use GPU flag here. And again, the fit and predict follows the widely popular scikit-learn API, so it can plug into any pipelines or applications which may be expecting estimators with those methods. Okay, so here's like a full worked example of training a logistic regression from SnapML and evaluating it. What we want to show really with this slide is that SnapML can plug into applications which are using the scikit-learn ecosystem. So that means you can reuse the data loading, the pre-processing, the model selection, and metrics functionality from scikit-learn. You don't need to implement everything from scratch or use new stuff from SnapML. You can simply replace the training part, replace the estimator from scikit-learn with SnapML, and all of the rest remains the same. Okay, so now we're going to talk a bit about the performance of SnapML in terms of training. So firstly, we have a benchmark comparing SnapML against scikit-learn for logistic regression, so very popular generalized linear model. We have 5 different data sets here. They involve various different use cases. We have computational advertising, financial services, retail, as well as scientific computation, the Higgs dataset. And we deploy SnapML on a fairly powerful server here, but we're only using 4 threads for each model, both for scikit-learn as well as SnapML. And what you see here is time. So there are 2 things we want to draw your attention to here. So firstly, all 5 of these data sets, the training time is significantly less, so more than a factor of 10, up to a factor of 121, sorry. And the next thing is to look at the AUC, so this you see on the test set. Now, generalized logistic regression is a convex optimization problem, so there is a single solution, and indeed most of the time scikit-learn and SnapML exactly in the AUC. A couple of cases where you see SnapML is better, and that's actually because the scikit-learn solver failed to converge. So as of the most recent version of scikit-learn, LBFGS is the default solver, and it's not converging on these data sets. So we could let it run for longer, and it might get to the correct solution. But of course, then it's going to take even longer than you see here. So the technology behind these speedups is related to the multi-threaded CPU-based algorithms I mentioned earlier. So none of these speedups are coming from GPU. I want to make that crystal clear. This is purely coming from our optimized CPU algorithm. And this was showcased in the NeurIPS conference last year, where it got a spotlight presentation. Okay, next slide, please. So again, similar benchmark, again, is CPU only, but this time engine tree algorithm from SnapML, comparing scikit-learn as well as SnapML. So here again, we see 6 data sets. Again, in the data sets correspond to domains like retail, advertising, and financial services. Again, we see some speed ups varying from 4x on Rossmann up to 30x on credit card. And here we have a mixture of regression and classification problems, because decision trees can be used for both. So in all cases, we see that the mean squared error is either lower or the AUC is higher for the classification problems. So we don't sacrifice any accuracy in order to get this acceleration. Next slide, please. Okay, so similar vein, this is the random forest algorithm from scikit-learn, so from SnapML and scikit-learn. So a random forest is an ensemble of decision trees. The random forest is a much more complex model than a single decision tree. So the absolute training times increase a lot compared to the previous chart. But we see that the acceleration factors remain similar. So we have a minimum speed up of 5x up to a maximum speed up of 31x. And again, for the classification problems, we see that the AUC is higher. And for the regression problems, the MSE is very slightly, here it's almost exactly the same, and here it's slightly better using SnapML. Okay, next chart, please. Okay, so in this chart, we compare against a different framework. So we also switch gears a bit. In the previous 3 benchmarks, we were looking at the CPU performance, and now we're looking at the GPU performance. And we're comparing here to the QML framework from NVIDIA, which is software for accelerated classical machine learning on GPUs. So on the left-hand side, we compare for ridge regression, which is like a L2 regularized linear regression, and on the right for logistic, for classification problems. And the y-axis here shows the speed up we achieved over QML. So we see in some cases, QML was ever so slightly better, and in other cases, SnapML was 164 times better. 68 times better on logistic. And these speed ups are coming from the fact that we solve the problem using fundamentally different algorithms than QML. And this is related to the core research technology, which is underpinning the SnapML framework. Okay, next chart, please. Okay, so now I'd like to talk a bit about the accuracy gains that one can achieve using SnapML, and in particular using SnapBoost, our boosting machine. So this is one of the first benchmarks we did with SnapBoost in the beginning, using the OpenML platform. So OpenML is like a platform for collaborative data science. It hosts thousands of data sets, which you can easily download using AI, which makes it well suited for doing these kind of benchmarks where it's very important to compare different boosting machines using a large number of data sets, because with a single data set, it's hard to say which one is really better. You need a large sample to be able to make conclusive insights about that. So here we took 48 data sets from OpenML, and we performed hyperparameter tuning as well as cross-validation to do generalization estimation. So we used a process known as nested cross-validation in order to estimate the test error correctly, as well as to tune the hyperparameters of all 3 models. And so on the left-hand side, we compare the SnapBoost against LightGBM. And then the red bars are the data sets when LightGBM was better in terms of the test loss. And the blue data sets in the bottom are the cases where SnapBoost achieved a better test loss, lower test loss. So we see that SnapBoost won in 31 out of 48. And in some cases, the improvement was very significant. Similarly, on the right-hand panel, we compare with XGBoost, and there we see a similar conclusion that SnapBoost achieved better test loss in 32 of the 48 datasets under test. Next chart, please. Okay, so here we compare SnapBoost again against XGBoost and LightGBM, but now on a different set of data sets. So OpenML is great for benchmarking because, as I said before, it has a lot of data sets, but the data sets are often quite small. And also they're very often synthetic or kind of toy data sets that people have been using in the machine learning community for quite some time. What we wanted to do with this benchmark was to take some more realistic and more interesting use cases. So we took 3 data sets from the Kaggle platform. So Kaggle is a platform where people compete to see who can find the most accurate machine learning solution for various different interesting tasks. So in this case, the 3 use cases we looked at was credit card fraud detection, and then a retail data set where the goal is to predict the sales of different stores, to the sales volume. And another is this Macari price suggestion, where you want to predict the optimal price for different products based on characteristics and customer preferences and so on. So as you may be aware, in Kaggle, often the winning solution is using XGBoost or LightGBM in some capacity. So actually, Kaggle is really where these frameworks made the name for themselves. And what we see here is that on all 3 of these use cases, when we compare the test metric, whether it's log loss or root mean squared error for the regression problems, we see that SnapBoost is beating XGBoost and LightGBM. And I'd like to emphasize that this is after hyperparameter tuning. So this is the tuned test loss for these 3 different frameworks. So again, this is our most recent research, and we just had our paper on SnapBoost accepted to the NeurIPS conference, which will take place in December. So please check out that paper for more details. Next chart, please. Okay, so finally, this is a real industrial application of SnapBoost. So this was a IBM customer in the financial services domain who came to us saying that they have a gradient boosting workload. They were actually using a different framework. They were using the GBM from H2O. That's about all we know. They wouldn't tell us the data set or the learning task, and they ran all of the experiments themselves. And this is what they reported back to us. Basically, they compared the H2O boosting machine, excuse me. They compared the H2O boosting machine after extensive hyperparameter tuning with the SnapBoost algorithm, again, after extensive hyperparameter tuning, both here running on the GPU. And they found that SnapBoost could give them 12% improved accuracy, and the end-to-end runtime was very similar. So the total time it took them to do the tuning was around 20 minutes in both cases. Okay, next slide, please. Okay, so now we're going to talk about the inference acceleration aspect of SnapML, which is again some of our very recent work. So the goal with inference acceleration is of course, primarily to accelerate inference, but we also want to do it in a portable way. So what we mean by that is if a customer or user has a model which they've pre-trained in XGBoost or LightGBM or maybe another boosting framework, we want to be able to accelerate the inference of that model within SnapML seamlessly. So we want to be able to score accelerated scoring for SnapBoost, for models trained with SnapBoost, but also we want to be able to import models trained with other frameworks so we can offer the same acceleration for XGBoost models and for LightGBM models. So what you see here is a benchmark on the credit card fraud dataset, and we have a model which was pre-trained in XGBoost. And on the x-axis is the depth of the tree, and on the y-axis is the inference latency. So this is single record inference. So we're scoring a single record at a time and sending it back to the user. And what we see in red, performance of XGBoost with 1, 2, and 4 threads. As you'll see, XGBoost is not particularly well, is not able to benefit from multi-threading particularly well for single record inference. Whereas if we import that pre-trained XGBoost model into SnapML, even with one thread, we have a significant speed up over the XGBoost scoring engine. And then as we add 2 or 4 threads, that speed up continues to grow. So in the maximum case, at depth 16, we have a speed up of around 4x. And you'll notice here that the speed up is growing with the complexity of the model. And on the next chart, we have the same benchmark, but a different data set. So this is Epsilon, which is a more complex data set in that it has many more features than the credit card fraud. And this is also running on a different platform. So this is running on IBM Z on the mainframe, Z14. So IBM customers run a lot of transactional workloads on such systems where they want to do, like real-time prediction using machine learning. And here we see an even bigger speed up. So using 8 threads, we have a 32x speed up over the XGBoost scoring engine. And again, this is the same model, so the accuracy is the same in all cases. The model was trained in a different platform using XGBoost and then imported into the SnapML engine and evaluated on the Z mainframe system. Okay, so yeah, we're approaching the end now, and just some of our closing remarks. So there's a whole lot of research which has gone into this package. Many publications in Europe, in ICML, a lot of workshop and talks. So please, if you're interested in the algorithms and their implementations, go and check out some of the papers. And next chart, please. So finally, we'd just like to talk about how you can try it. So how to get SnapML, how to install it. So if you remember in the beginning, we said that SnapML is currently available through Watson Machine Learning Community Edition. So at this URL, you can find the instructions for how to install Watson Machine Learning CE. It's very simple. You simply subscribe to our Conda channel, and then you can install, say, the Py4sk package using Conda install Py4sk. We have packages for Power as well as x86, so this is not IBM specific. You can run on any x86 machine, but right now we're specific to Linux, so we don't provide packages for Mac OS and so on. As I mentioned before, we're working on the PyP packaging, so we hope that later this month or next month, it should be possible to install SnapML via pip install SnapML. You can find the latest documentation at this URL, as well as tutorials and examples at this one. And we have some video tutorials here, and you can find out more with all of these different links at our project homepage, zurich.ibm.com/snapml. Okay, I think that brings us to the end of the presentation. Thank you very much for your attention, and please reach out if you have any questions or interest in SnapML.
Thank you, Tom, and thank you, everybody. We hope you enjoyed this presentation, and thank you for your attention. Bye.
Goodbye.